Okay. Okay. Uh, Good evening. So welcome to the last session of the course, Introduction to RL. And as we know, we have completed all the classical RL algorithms and also the modern algorithms like policy gradient and neural networks and so on. Today, I'll be showing some modern trends in RL, mostly how you people can do safe RL, that is taking actions in a environment where you can guarantee safety or something like that, so that you don't, when you deploy a robot or something, it does not break trying to learn from the environment. So we'll try to do something like planning, and we'll do what is called curriculum learning. These are the two things we'll try to do. So let's get started then. So if you recall, what was policy gradient? What was policy gradient? Policy grade. Yeah, tell.
So we had the probability function for the maximum likelihood of the action that we got from learning. In RLV, the neural network would give us the probability distribution for the optimal action, and then we would differentiate it with respect to the
That is
W.
fine. What is that? Those are all optimization. That is fine. The idea is, given a state, you want a distribution over action.
Yeah, optimal action distribution, and that's what I'm gonna find using gradient descent, and that's why the term gradient, policy gradient, because my policy is what I want to find, and it depends on the weights I multiply. So policy gradient, yeah.
Gradient ascent, because you have to maximize reward. No,
Yeah, sorry, gradient ascent.
same thing. This is, you can always do what you can invert the loss and then do gradient descent if you like that. If you want to use some iterator, fine, no problem. What I was saying is, so L theta was defined as, so theta is the policy network, to be exact. This is the summation over, say, all states. Let's write it in terms of expectations first. First expectation, there'll be another expectation, that is, given state and action, what is the GT, or the return function, total reward. We used RG, all of these. So we used R thetas, things like that. So the first expectation is, this will be an expectation. This will give me a function of state and action, that is current state and action. And then the outer expectation will be, action will be, you will sum over all the actions, yes or no? Given
Yes,
the
sir.
state, yes. So this will marginalize out, will remove the action. So this function, this entire function, double expectation, would be a function of which random variable?
Yes.
Correct. And therefore we need, since L theta, we don't want it to be a function of any random variable, we will also take an expectation over state sampled from some initial state sampled from some distribution mu. So therefore we said that, okay, fine. When we expanded this, rather, this was equal to state from the initial sampling distribution, action from the policy distribution, and the S dash from the Markov chain, isn't it? The controlled Markov chain. Fine. And we saw this was the expected value of the loss or the reward. And we saw this was defined as L theta. This is what we wanted to do. We want to maximize total reward. Then we took the derivative of L theta because we want to do gradient descent. And we found that this expectation basically changes into an expectation over the stationary distribution, no?
Yes, only the stationary distribution and a term called ln pi of theta.
Correct. It's the same. So this entire thing that I had, this stationary distribution comes in because we are going to move on in the Markov chain based on the policy. So this is d pi transpose p pi is equal to d pi transpose. This is the stationary distribution of the policy pi. So we saw this was the stationary distribution and we took the derivative, we did the recursion. And after we completed the recursion, what did we see? We saw that it was q pi of SA and the gradient with respect to q pi of SA and the gradient with respect to log of pi theta of S, A given S, isn't it? And we saw action was again sampled from pi theta distribution. There's an expectation over the policy pi we are learning, and S dash was sampled from the Markov MDP, isn't it? Right? Transition probability. So therefore, we said that our algorithm was the reinforced algorithm. Algorithm said that theta t plus 1 is equal to theta t plus alpha t q pi of S comma A gradient of log of pi theta A given S, where this q pi distribution was
Yeah, I estimated it by taking trajectories and
correct.
expectation of the long-term rewards,
Correct.
GT.
Using trajectories and Monte Carlo sampling. This is what we did last time. Very good. So this is q pi. So for example, S0, A0, S1, A1. So in between you will have a reward S0, A0, S1, A1, S2, and so on. Fine. So once you have this, the reward of S1, A1, S2. So we will say that q pi of S0 comma A0 is nothing but reward of S0. We have already did this first visit method, second visit method, and so on, isn't it? Already done this using first visit or every visit method, isn't it? So we can just estimate q pi this way. So now, just a moment. Huh? One moment. So, so this is what we have done, and I think all of you are aware of that. Now what I'll try to show is I will try to remove a baseline function somehow. So what is this? Why am I trying to remove this baseline function? Will be becoming evident when we turn to actor-critic methods. But let us try to see that these two that I have are equivalent. So again, we want to remove a baseline function b of s. Importantly, independent of action A. So if I can remove any function which is independent of action A, then I will say that these two gradients are the same. They are equal actually. Let us try and prove this. Q pi of s comma a minus bs theta of log of q pi of a given s. Let's just take an expectation with a given pi theta of s. Okay, just this much. So can you tell me how do I use Lotus to expand this? Sunday?
Summation uh, mu of oh,
Okay. Mu of pi of
pi of a given s into
okay into this
yeah.
Lotus. Q pi of s comma
uh,
a minus ps.
One question, like
Yeah.
when we had written the like gradient descent, so I
Hmm.
remember that it was the expectation over the states of d pi, right? So like
Hmm.
I didn't follow for a while. So how did it become expectation over action? Uh,
Expectation of action is over this pi theta. So initially also we had an expectation over action, no? So okay, let us go back to the basics. Just write it down then. This entire L theta will try and derive once again for the last time in the course. Good revision. Just look at this. So if I want the term average reward, I can do something like this, no? V pi of s given s, and then the expected value over the start state. S0 is equal to some d pi, say, the same stationary distribution. Is this fine? First step. And we say that this is the total sum L theta.
yeah,
Is
then
this
we had yeah,
correct? And this is an expectation over, just check this expectation. So V pi of S, V pi theta of S, this is again, I can write it as a summation of V pi S, V pi theta of S. Yes or no? By Lotus.
remember.
Okay, so that is great. So again, this is a function of S, that will be just pi theta of S. That is all fine. So I think I made a mistake. So this is be just expected value of pi theta. It didn't correct me also. Nice. So see, because your V pi theta is defined as the expected reward.
I mean, even if we took an expected double
Yeah,
expectation,
it's correct. It was constant. You're right. This is how it is defined, right? The given a reward, given a state, what is the long term reward? Okay. So now this is basically what? This is the expected value of, again, I can condition on another random variable over here. First of all, we will do our trick. No, not this. For this case, I will not do the trick. I will just write the Bellman equation. Let's try and do an easier method. And I sample from S comma A. And this action is sampled from P theta of, okay? Correct. Fine. So all I'm doing is the inner summation. I am conditioning, again conditioning on A. And then this expectation marginalizes A. Okay.
Yeah, got it. Actually, the thing is like if we like wrote the now this in the expectation for like summation probably mu of d pi of s into pi of as a given s and then q pi of uh,
Mhm.
if we wrote the entire thing using Lotus now after deriving Bellman and then we
Mhm.
differentiated it and like in the final expression we were actually observing the q pi of a given s given q pi of s into pi of a given s
Correct.
because that's how we got the log
Correct.
but the sum over the action would still remain so
Correct.
that's what I like forgot so both the sum over the states and the sum over the actions would remains.
Correct. And then a better, easier way to remember this is a trick, I would say, is L. So if you, all the derivation and all is fine, and this is it's a nasty trick, but do like no problem if you try using the trick. So you write this as summation of d pi of s pi of pi theta of a given s. So again, just trying to use the equation here, the dagger equation. From dagger, I get d pi of s p pi theta of s and s in s. And this is equal to summation of d pi of s summation of pi theta of a given s q pi of s given a. Fine. So now an easy way to remember is gradient of L theta is, see, just this depends on theta. So you just write down given as q pi of SA. So the idea is saying this is not correct, but saying this is independent of theta. Never tell this to people in an interview, then they will say that you don't know the thing. But this ends up being the same thing because we get the stationary distribution coming in. And we see that we using the infinite recursion, that q pi theta and whatever we had, we could remove them into just summations. So just derivative, when I say that since I've written theta here, this is a dumb way to remember, and then I'll just keep this as log of pi theta of a given s into pi theta of A given S. So that's what I had written down. So therefore, we have two expectations or expectations over S in d pi, A in pi theta, and S dash in. And this is log of pi theta of A given S. Okay, so this is what the Bellman equation and the policy gradient is.
And the pi of A given S would be observed. So V pi of S, like pi of pi theta of A given S into Q of S given S and A. So that would become V pi of S.
This one.
Yeah, like we already like divided and multiplied by pi of A given
Ah,
S. So
correct.
pi of A given S into Q of SA is V pi of S.
Correct. I have just taken expectation of it. No,
Okay,
I
okay,
will
yeah, yeah.
not.
The same thing here.
So because we will do Q learning sort of a thing or some way where actions are also involved. So basically, what am I doing? I am just dividing.
That's why I was saying that, like, because when we were in the last class, we had written V pi of S, and
Correct.
then it
Now,
was coming.
correct. We wrote it in terms of V pi of S, and then we should do the recursion, and it was the same thing that was coming up. No, that the
Yes, maybe.
actions, the summation
Oh,
over the actions still remained, and we
yes,
got back
no.
V.
Yeah, the summation would still be there.
Correct. Right. So now let's do what the baseline function is telling me. Very good. So let's try and do the baseline function. So see, this is equal to saying pi theta of A given S into gradient of pi theta of A given S by pi theta of A given S. I took the derivative of the log into q pi of SA minus BS. This and this gets cancelled. This is equal to summation of gradient of pi theta of A given S, q pi of S given A over actions in S, and you have summation of BS gradient of pi theta of A given S. Again, A in S. So see the first term, term one, is still the same reinforced polar gradients, yes or no? The first term, you can still divide by pi theta of A given S and multiply by pi theta of A given S and still have the expected value of A given pi theta of S, q pi of S comma A, gradient of log of pi theta of A given S. Yes or no? Correct? The term one. Now the second
Yes.
term, if the second term is very, very interesting to see. The summation of A given S, B of S, the gradient of pi theta of A given S. See this BS, why I did not want it to be a function of action is because I can take this out, right? Out of the summation. Because it's not a function of action and I'm summing over actions here.
Yes.
So, and similarly, this is linear. Gradients are linear. Are linear operations. Derivatives are linear. What do I mean by derivatives are linear? So ddx of f1x plus f2x is the same as df1x dx plus df2 dx, isn't it?
Yes.
So I will take the gradient outside and take the summation over all actions in the state pi theta of A given S. So this, do you agree, is equal to 1? And why is it equal to 1?
Because it's a probability distribution.
Very good. This is a probability distribution. So this is equal to 0. The derivative of 1 is equal to 0. Fine. So what I'll try to do now is we'll try and use this property. So first of all, I can remove a baseline from this. First of all, reinforce with baseline, reinforce plus baseline would just be theta t plus 1 is equal to theta t plus alpha t q pi of s comma a minus some reward baseline gradient of log of pi theta of a given s. This I can do. Why will I do this? Because if I want that this are too high or low, I can remove an offset. Clear? I can do that. We do it all the time in normalization and things like that. So I can remove an offset. So I can remove an offset and still divide by some value and still get the same thing because I have a learning rate constant in front of me. So I can sort of normalize z-score the values. Just remove the mean and divide by the standard deviation. Things like that I can be done over the rewards. Isn't it? So basically what I'm trying to say is theta t plus 1. This is reinforce plus baseline can be theta t plus alpha t q pi of s comma a minus say the mean reward you know in the environment reward and say you can divide by the standard deviation and you can still get pi theta of log of. So this is basically called a z score. We have already seen this. No, x minus mu by sigma is the z value. What is the value in the z scale? So why can I divide by sigma? See, this can be written grouped together and written as alpha t bar. As long as it is a constant, it doesn't really matter. Clear? These are the things
Yes.
why I can. These are the things why I can do these reinforce with the baseline normalization. That is fine. So once I do a baseline normalization, now I come to what is called as a actor-critic method. So what is currently happening is currently, I was trying to learn from q pi of s comma a directly, needing us to store the entire trajectory, yes or no? Or some dynamic programming. So no update at every step is the problem. But TD-based algorithms, TD-based algorithms are beneficial because we can update at every step. Let us see how we can do that. Currently, I told you that the gradient of L theta can be written as the expected value with all the relevant random variables. Now you should be able to tell me what are the random variables, but so we're not going to write it. Q pi of SA minus a baseline of the states log pi of A given S. Correct? Now, I will
Right.
say that this BS is a value function. I'll say what WN in a service, in a while. Let BS be the value function. This is how actor-critic algorithm was developed. Okay. So let's say it is still going to hold its any baseline function. So it can be a function of S, just cannot be a function of A. Correct? It's still independent of A. Fine.
Yeah, fine.
So you see, I can still do even better than this. Q pi of S comma A can be written as summation of the rewards t equal to 0 to infinity st at plus 1 given S comma A minus VW of S into the gradient of log of P of A given S. Do you agree? This is just the definition of Q. Once I write the definition of Q, I can write one more step. What is that step? The expected value of the reward of S A S dash plus gamma times. Tell me V pi of
S dash.
given S comma A minus VW of S. For the timing, let's keep this pi. So this will help you to understand real function. No problem. V pi of S. Okay. So let this leads to be the oracle value function. So it currently knows oracle value function. It clearly knows somebody has told you what are the value of every state, and it has known these for a long time. And we are using them as constant values, no problem. So this becomes, you see, there's two expectations again. So I will remove all the expectations into a single expectation. Reward of S A S dash plus the discount factor V pi of S dash minus V pi of S into the gradient of log of pi theta of K given S. Okay. Now do you see a resemblance? Tell me all the random variables one by one. S is sampled from D pi. A is sampled from P theta. S dash is sampled from the MDP. These are the random variables. Okay. So at a time t, I can write this as the expected value of the reward at st, at st plus 1, gamma v pi of st plus 1. Now, can you tell me what can I do? How can I write this? How can we know these value functions? But the oracle is not actually known. There's no free lunch. We have to learn it also. Also learn it, isn't it? So how do we learn it? We have discussed all these in the past.
Yeah, so like this resembles kind of a TD, and
Correct.
like so we would be doing a TD lambda approach or a TD01.
With function approximation or whatever you want. Say I will approximate this using VW. All the while we used them as phi transpose ST plus 1 into W. This can again be a neural network. As we discussed last time, can be an MLP, can take a state and give you the value function. Again, this will be VW of ST. Great. So now I have theta t plus 1 as this is the update, policy update as theta t plus alpha t st at st plus 1 plus VW gamma times VW st plus 1 is an example. Okay, clear? Now, once I know this I can write as delta t at a time t and simplify this as theta t plus 1 is equal to theta t plus alpha t delta t and the gradient of log of pi theta of t plus t. This is my policy update. But now remember, I also have a something else to learn, right? What else do I need to learn? W needs to be learned, no?
Yeah, so by W do you mean the optimal policy?
No, W is the neural network. So I'll draw it over here. I have drawn it anyways. I'll show you this.
Okay, got it. Like we are also like this is like from the states we are finding a yeah
The value function.
linear yeah, value function, and from the value functions we are finding the probability of the actions like
The
policy
policy.
the policy by back
So
propagation and everything. Yes.
correct. This is called the critic network. We'll integrate it. The critic network tells you the value function. And this is called the actor network. That is, takes decisions in a noisy environment. Clear? So now let us try to integrate them. So now, how do I learn VW? People who have attended function approximation based value functions.
Yeah, so first of all, like from the states, I'm gonna do a feature extraction, and then
Correct.
I have those phi of s's.
And this
Now,
is think that it is phi of s. It does everything
yeah,
is
the
done in
phi
the
of
neural
s.
network.
Like,
In the it is correct.
yeah, if I have a say an s, like just so as to be clear,
Correct.
from the s we calculate the phi of s, and like we have obviously a linear function to like we have a function to approximate get features, so
Hmm.
it can be anything, right? Like we use
Correct.
convolution as well for feature extraction. Once we
Correct.
have the features, then we are gonna do a linear combination again, summation of
Correct.
wi phi of s,
Hmm.
and then that's how, and that's what we are gonna then again optimize, do gradient descent, and then now for the w's, and then calculate vw of s, and then we'll again optimize for the theta when we know the VW of S.
Correct. So this will be an alternative optimization. Let's see how to do that. So you will have all these features and I will just output, one node will output in a neural network what is the value of the value function. So basically we have done this in the class before. So W star will be obtained from argmin of the real value function minus VW, the D norm. Remember? Which was equal to summation of d pi of S, p pi of S minus dw of S squared. So I take a derivative. So say this is the loss 2, loss critic. So DLC dw will be just the expected value S from d pi. Can put a half as well. P pi S minus ds into gradient of. Yes or no? This is fine. I just took the derivative of this. So only the inner VW depends on W. And we will have the same expectation because of the d pi. Very nice. So now once I have this, I can also replace this. We have done this before by the same terms, same expectation. This can be written as RST AT ST plus 1 plus gamma times V pi of ST plus 1 minus VW dash of ST gradient of W VW. So now this is approximated using VW dash ST plus 1. Clear?
Yeah, clear. That's why I was thinking why you are writing V pi of S because we don't know pi.
Correct. So this
And
is
here also, like the d pi can be anything, right? It can be anything, right? Because we
d
don't
pi
know.
is the station. No, it will be the stationary distribution, no?
Oh
So
no,
it depends
sorry.
on the,
Does
it will
Markov
be
chain? It depends on the
correct.
Markov.
Stationary distribution of p pi. That's why we did the Markov chains in detail because that's what will be used. So now you'll see the WT plus 1 is the same update, isn't it? The WT plus some say beta T, delta T. Clear? So this is the critique from the star equation. I'm putting the star over here. Right? This is gradient descent. This is gradient descent. And we keep doing this iteratively. So we keep doing this iteratively. The actor learns and the critic learns. Once you fix the actor, update the critic, fix the critic, update the actor. Right? Therefore, it's called an actor-critic network. How do you do this? You can clearly see this from this diagram that I have. So given a state ST, I pass it through the policy network or the critique network or the actor network. This will give me an action AT plus 1, which I represented as 2. Then I pass it through the environment, observed the reward, pass it through the pass ST plus 1 and through the value network and get the delta, right? The delta T. And the delta T is being used to learn pi T. Do you see questions regarding this diagram? You want to a particular uh, particular arrow in this flow chart you want me to elucidate?
From ST, the arrow connecting VW is how it is coming. You said that it is coming by the or I mean, by the cycle to VW. Then directly also we are using to VW.
Correct, because you remember dt, delta t depends on what? Delta t depends on r of st, at, st plus 1. Correct? The delta t is a temporal difference. Vw
Yes.
st plus 1 minus Vw of st. This is my temporal difference.
Okay.
Correct?
All right. Yes. Yes.
So to compute the temporal difference, I need both st plus 1 and st, and also the reward from the environment. And the reward from the environment in turn depends on the action that the policy network takes. This is not at plus 1, this is 18. Sorry. Okay, so you start off with this step 1. I'm going to write it in red now, so that you can understand what are the steps. So step 1 is the state going into the actor network. Step 2 is the action being selected. Step 3, observing the reward. Step 4 is passing st plus 1. Step 5, passing st. Step 6, giving delta t back. Step 7, also giving st plus 1 back. Right. That's all we want. And then once we get st plus 1 back, 8 will be to predict at plus 1. Clear? And we have written down the equations. So when we update this actor network, fix the critique. When you update this, fix the actor. Any questions before I go into safe RL? So this ends normal reinforcement learning. And we'll now use all these methods that we have already learned to do a couple of algorithms in the domain of safe reinforcement learning, particularly planning and curriculum learning. Planning is very simple, but before I go into planning, do you have any questions? Okay. So let's see what planning is. So the high level view of planning goes as follows. Say you are going to take a decision or take an action, which will take you to another state. Fine, but you may get a very, very negative reward when you take an action, right? Which may end the life of the actor in itself. So for example, would you jump off the cliff to see what reward you got? Because it may break your bones and the worst case can kill you, right? You would not jump off the cliff because you know that if something falls down from super high, it's going to break, right? Because of the momentum it hits the ground with. Right? You would not see that, you would not actually, the idea is RL agent need not always explore every state. Right? And
Yes.
actions. This is the basic idea of safe RL. And how do we limit our RL agent from taking dangerous actions or going to dangerous states is the discussion for safety in RL. Very important, because if you want, for example, to deliver a robot to moon or something like that, you want to plan beforehand, do something so that it already knows the value function when it has to reach there, and you don't want to learn online. Similarly, you have a car. Your car wants to go, self-driving car wants to go, it must know that what happens in certain states beforehand without actually going and crashing. Right? These are the few things we want this to happen. So we can do it by planning or learning from the experience of a teacher, somebody So people in real life, what happens is you learn from mistakes people have already made, which means that you already are you're already aware of the knowledge of a particular action or state in the environment. So that helps you to plan or helps you to select teachers which will actually tell you that you should not take these actions. And we'll try to formalize how are we going to do that so that the agent learns in a safer environment. Motivation is clear. The first we'll be doing is called planning. And we'll be doing it based on an algorithm called Dyna, proposed by Sir and Barto again. So look at this diagram that I have on the left. So for your value function, learning from value function directly is called direct by active RL. So what you do is you take the value function, select an action, and you see this action reacts with the environment. You get an experience that is a reward. And using this reward signal, your value function is trained. And once you have this experience, you can use, so not only your experience, but also accumulated experience can be used to save a model. Save a model of the world around you. So without taking an action, you never know what's going to happen. You may have to come up with theory, but you have to, at the end of the day, have to have some model of what is going to happen. And that model, say you know from experience, that you have, so that you don't commit same mistakes again and again. That's the idea. So from the past, you know that this is a wrong action to take. Therefore, you save it in a model of the environment, and then you think. Based on the model of environment, you think whether I should take an action. That is called the idea of planning. Is it clear? Questions?
Yes.
Okay. So how do we learn? How does this planning work? So you want fewer, as I was saying, you want fewer interactions with the environment. So I'll try to learn it using, say, Dyna-Q learning algorithm. So let's use what is called Dyna-Q learning. And we'll assume a model-free tabular algorithm. Tabular space, state space. There's some countable. If it is not countable, you can use your knowledge of feature extractors and things like that to get it into a countable space. Okay. So what is how is Dyna expanded? I'll just check. This comes from the fact that you are in a dynamic environment and you don't want to do just save this say use the environment always to dynamically act with it, and you want some predetermined experience. Let's see what does that mean. Normally, what do we do? Say,
Acha, like, is this like, suppose we are trying to learn some like medical data and we don't have enough annotated data. So we can take a like already trained say ResNet and uh, or one of those like very popular the already trained and then we would want them to want the agent to take the help of the like already defined
Yes,
model.
you can do that.
So
You can
is
always replace these. As you are
so
saying, you
it's
can, this is, tell me. So it is?
so it is like a encoding on top of a already made a network which already trained. Uh,
Network, but correct. But first, let us try and understand it's without even going into that complexity. You're absolutely right, that analogy. But let's try to do a tabular case first, and then we'll try and understand what is happening. So normally in model free Q learning, what do we do? What is the thing that is first done in a model free Q learning? Step one,
for asynchronous, right?
yes.
Yeah. Then we just take an action and sample a reward and then choose the maximum action that we get.
Mhm.
Uh, and then we go along that path into that state. And then again, just keep on selecting maximum action from select the action which gives me the maximum reward, which
Okay,
started
generate,
from sampling.
correct. So let's formally write it. Generate a trajectory S0, A0, S1, R of S0, A0, S1, S1, A1, and so on. Fine. So now for a particular state ST, I take an action AT, reward is ST, AT, ST plus 1, and I go to a state ST plus 1. Right? So once I have this, what I do is, first of all, in Q learning, AT is selected by, say, a epsilon greedy policy over the Q value functions S comma A. Correct? You know what is an epsilon greedy policy? This is equal to argmax of A, Q pi of SA, ST I should write because I'm taking action T, with P equal to 1 minus epsilon uniform A1, A2 dot 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 AN with P equal to epsilon. Fine. So what is epsilon greedy algorithm? So once I go to do that, so I at state ST, I select an action. So the trajectory is generated this way. I select an action AT, observe ST plus 1, which is sampled from the my MDP. Then what I do, I write Q pi of or Qn plus 1 ST comma AT as Qn of ST comma AT plus alpha T, or rather nth update it is. So alpha N reward of ST AT ST plus 1 plus max of max over all actions Q of ST plus 1 minus Q of This is what I do in Q learning. When I don't have a model and I am doing asynchronous based on a trajectory. That's fine. Okay. So if it is fine, what I'll do now is I will also save this as a deterministic table. So what do I mean? So I will do something like update model with st, at, st plus 1, reward t plus 1, whatever. Okay. So this is what I'll do. So this is the planning. So all heuristic at the end of the day. But what is basically, this is something like this. So say you start from an action state X. So say you take an action A and you observe a reward R and go to state Y plus 1. So what is actually done is you maintain a table like this for X to A. So basically this table will map from st comma at to st plus 1 comma rt plus 1. This is fine. This table maps to this and it is assumed deterministic. Fine. Table is again a function at the end of the day. It's a mapping. Questions? As soon as I see a state, action, reward, and next state, I can put it in a table, yes or no? The normal Q learning happened up to this. This is normal Q learning.
Yeah, the normal approach is clear. Like I just didn't follow the last few 1 minute.
So what I was trying to say is for a particular state and action at a current state, when you interact with state in state st with action at, you observe st plus 1 and reward of st at st plus 1 is equal to say rt plus 1. This is what happens. This is clear. So I say that update a table such that t of st comma at will return st plus 1 and rt plus 1. Is that fine?
Yeah, I'm just making a state and reward table containing the rewards I have gotten.
Correct.
At
It's
this.
just making a database.
Yeah.
For a particular state and action, I'm seeing what I observe for the next state and reward. Fine. So now what do I do? This is what I had written, planning. So in planning, use only the table. Say you have 5 steps of planning in 1 step of interaction. So what you do is randomly sample st comma at from the table and update Again, Qn plus 1 of st. Instead of writing st comma st, I'll just write s comma a. S comma a as Qn of s comma a. I'm just not putting the t's in planning, and I'm putting t's in non-planning states. So it will be easy for you to understand. Clear? So basically repeat n times. So you can put this k steps in one step of planning, repeat k times. Fine. So this entire algorithm looks something like this. So where you have one step of Q learning based on ST, AT, reward of ST, AT, ST plus 1, ST plus 1, step 1. Step 2, the table of S comma A, you save as, or ST comma AT, you save as the reward ST, AT, ST plus 1, comma ST plus 1. Step 3 is K steps of planning. Iterate, randomly sample S comma A from table T, Q learning update based on SA. Iterate until convergence. Questions? You have to ask. Is it clear?
So when will we select from the table and when will not?
That's what I'm saying. No, one step. This is a loop for I equal to 1, 2, dot in ni. Say ni be the number of interactions. Okay. Even there should be more loops actually. So this is the end of the trajectory, say capital T. And then you will have for I equal to 1, 2, dot ni. This is the length of trajectory. Again, trajectory, I same notation, let's say tau, trajectory length.
So for like all these tables will be the state specific, right? When if,
But you don't know the state space, no? That's why you're saving the model.
yeah, like suppose that this like T of we are storing the ST plus 1 and the RS and the R that we get,
Correct.
like RT, yeah, the RSTAT and the ST plus 1. So we need to also when we have vectors for every STAT pairs or like pair
No.
vector pair int.
So this can, that's up to you. Can update, rewrite, average, and so on. People just rewrite. Take the recent one. You can take two of them and keep the average and store the best one, and so on. This need not be a vector. This will just be a reward and a st plus 1. For a particular interaction, this is just one value, isn't it? For a particular interaction, this is just one value, and that's what I'm saving. So for if again with the same action and state, I get a different reward and go to a different state, I will update the table to that. Because the primary key.
When every step of the Q learning, like this is like for every step of Q learning means like for every one transition we are gonna do k steps of planning.
Correct.
So, but for initially we won't be having.
That is fine. You can. That is all your hand. That is in your hand. You can put a warm up step like 10 times. I will only interact and then, or you can have a model of predetermined model which you can import. Transfer learning.
Got it. Then
those things are in your hand.
Got it. Then we'll do a Q learning, and for each step we are gonna do k steps of.
Correct. Planning again is Q learning itself, but planning is Q learning from the model. Okay.
Yeah, so like this but the Q learning we would be doing, like this is gonna be model free or
model free. This is model free. This
Okay,
is this Q learning. Yeah. This does not depend on any model. Correct. Because we are doing the update asynchronous model free null algorithm.
Yeah, so like this Dyna thing is entirely for like we are doing model free Q learning, but we introduce a model for every step. We are doing k steps of planning.
Correct. So basically, there are two components to it. This is this model of this environment, and there could be a one that you were doing a planning on. That is, on the model you'll do a planning, and the experience you do a real Q learning. That's the idea. So as you were saying, so if this is tabular, so for a continuous setting, what will you do? Give me some ideas. These are open questions at the end of the day. Continuous state space.
Again, we have learned how to like solve these issues. Continuous state space calls for function approximation.
But table, how will you store? There are a few options over here. There are two options.
Store phi of st plus 1 in reward.
But that is an uncountable set. How many will you store? Isn't it? You cannot store it in terms of a table because it's an uncountable value. Phi of st. Continuous state space. So your st, at, st plus 1 and reward. You can train networks. First of all, which will take st and action at. And just output st plus 1 as one network, and the other network would be outputting, say, the reward. There's some transition function, say. So say let's model transition, and this is modeled reward. This models P of S given A, and this models. Okay, this can be done. This is one step. See, given this input, you are outputting these two values, correct? And then you can learn it by backpropagation similarly. But again, this is a method, or you can use what is called as quantized vectors. So say you have 10 quantized, 100 quantized, 1000 quantized vectors for state and action pair. So say this S comma A could be some R100 say RD space, and you save say K may much greater than the dimensions of quantized vectors.
So it's like converting an analog signal to a digital signal.
Correct. So if say you have quantized signals like Q1, Q2, dot 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 Qk, you will update. So for given a new state phi of st, you will take the transpose with Qj and you will take argmin of j, that is your Q star or the current quantized state. These are the few things that you can try and do. Few solutions. Again, these are open questions, papers have been written. And this is what I can understand and I can do if I am told to do this question. Finally, the other set of algorithms that we're going to study today is called curriculum learning. In curriculum learning, what happens is this is again a teacher-student algorithm. We have done actor-critic algorithm. Now this is a teacher-student algorithm where the teacher devises a strategy for students to learn in a dangerous environment. Okay, the student acts with the world around it. This teacher and then the student. Fine. This was a very recent paper, 2020. This is a project. I did my course project in RL on this paper. So I'll just briefly tell you what this thing is about so that you have an idea of the recent frontiers in reinforcement learning. So is the teacher's objective and the student's objective largely clear? For example, if you're trying to ride a bicycle, right? If you're trying to ride a bicycle, okay, so this bicycle that you have, and if this bicycle is going to fall, this is tilting, you will end up falling learning. But what used to happen in your childhood days? Do you remember how you learned to ride the bicycle?
Yeah, someone would hold it from the back.
Correct. Your mom or your dad or your elder brother would hold your bicycle from the back. Would reset to stability every time a teacher, could be a mom or dad, would reset the stability every time they felt you were out of control. Okay, it is true. It is true in any aspects of life. People who know more than you, they're more experienced, that keep telling you the device curriculum for you or device try to take you out of states or actions are in those or states or actions taking you to potentially dangerous states. So that's what is called a curriculum. So they could reset the stability every time you were going to fall. So this is the teacher and this is the student. So this is what used to happen. So the teacher's goal is to create these curriculums and the student's goal is to learn a policy. Student should learn an optimal policy safely. Okay. With limited efforts from teacher. So we don't want the teacher to always keep holding to the cycle. We want her to or him to release the cycle when they think that their child has learned. So these things have to be taken care by the teacher and the student. This is the motivation that the paper gives you. So and to do this, what they try to say is they define what is called a constrained MDP. First of all, what is an MDP? Do you remember? An MDP is a four tuple of states, actions, rewards, and probability. So we have done all of these. We have discussed these. So probability took an action. It took your state, comma action pair to a distribution over states. Right? Distribution over states. Rewards was a mapping from states, actions, and states to real numbers. So in addition to this, a controlled Markov chain, CMDP. Again, sorry, this is not controlled. This is constrained Markov chain. Constrained Markov decision process can be written as states, actions, rewards, probability density, probability control Markov chain probability with something called as D. D is the set of unsafe states. And as you can see, D will be a subset of S. Fine. Questions? So you have states, you have actions, you have rewards, the probability transition matrix, and you have a set of unstable states. We'll try to get the intuition, not solve the entire problem because it includes partially observable things like the environment and so on. But we'll give you a flavor of how to do that. So the objective of the student is to learn. Again, we have seen many RL algorithms objective is to maximize the reward. Maximize reward. Constrained by maximum number of times it goes to dangerous states. Questions? This is the objective of the student that we want to learn. Questions you have? Is it clear till this much?
The less than equals to pi.
This is some kappa, K. Some constant. This is a constant. That is, you don't want to go to a dangerous state multiple times, more than a constant number of times. Okay. Arbitrary, which could be arbitrarily small. Here.
Yes.
So now the student is interacting with the environment. Teacher does not know so much about the environment. Teacher, like humankind, must update the curriculum based on the performance of the student. So this is what happens. So you have the teacher, you have the student. Student will interact with environment. This will give us set of interventions or curriculum. This will tell you what to do and what not to do. And the student will return a performance. And the teacher will try to select a policy, a teacher policy that maximizes student performance. This is what we do. Our teachers teach us, and then based on how we do, they try, or how we understand the topic, they try to update their teaching methods, right? Questions? Curriculum induction by teacher. The teacher keeps updating based on the outcomes of the student. That is the solution, overall idea. And how do you do that? Is how which we'll be seeing in a little bit of high details now. We do it by using something called as the intervention set. Okay, the intervention set is a set of pairs of dangerous state and reinstatement. So what did I call this? The teacher would reset distribution. So let us try to understand what it is. So DI and TI, fine. DI is a set of dangerous states, potentially dangerous states. Why do I say potentially dangerous states? Can you tell me?
Because the teacher doesn't know the environment.
Correct. So DI is a set of potentially dangerous state because this is what the teacher guesses to be potential, guesses to be dangerous. Fine, very nice. So for this, what the teacher does is, for TI, the reset distribution is something like this. The reset distribution tau TI maps from the states in DI to the remaining states, that is states minus DI, that is maps to a probability distribution to the states, remaining states. So what it basically does is TI S from, or S dash from S, summation of S dash in, this will be equal to such that S belongs to DI. Domain is only DI. In the dangerous states, this is the transition matrix. Tell me, what will it be?
Like, it should be one, right? Because that S dash
Correct.
di, I'm just summing over all the S dash di states. Sorry, S minus di states.
Yes. So the Ti takes you to a safe state with a safe within quotes as deemed by teacher with probability 1. So basically, when we learn this, people show that if Di is a superset of D, then there exists a student who learn an optimal policy. That is fine. That's clearly, you can see if all the dangerous states are are in the potential tau i's or in the intervention set.
Rather, like, cannot the student go from one dangerous state to another?
No, that's what I'm saying. The teacher will as soon as the student say this is a dangerous state, as soon as it reaches a dangerous state, the teacher will just take it out of the dangerous state so that it doesn't get a negative reward. And it will
All
not
right.
give it a negative. The teacher will take care that it does not fall off the cliff and so on. But it will sort of give you a soft reward or tell you that it is not right. So now let us try to understand what a student constrained Markov chain MDP would look like. Okay, let's learn. Not a difficult thing. Say at time I, this is defined as this tuple of states, actions, PIs, RIs, D and DIs. Remember, our original Markov chain is original, and this is induced by teacher at time I. Original Markov chain was SAP, reward and danger states. Okay. So now you have to tell me for this environment, what should be PI? PI of S dash given SA for the student. So that the above intervention set Ti, Ti is validated. Can you tell me? If S belongs to states minus dangerous states, small s, then what should it be? Yes, on original MDP.
And if
Correct?
they are in yeah, and if they are in di, then it would be t of I, right?
Perfect. Others, did you understand? See, if in dangerous state, teacher will take over. Okay.
Yes.
Similarly, okay. So the PI is done. What will be the reward? reward of ST, AT, ST plus 1, or let me write SA S dash will be
Normal for the first case.
okay. SA S dash for S belongs to S minus DI. This is RI. And say R of SA S dash, say 0.05 or epsilon percentage. In the paper, they take epsilon to be 0. That is, they don't give any negative reward. But when I implemented, I saw that if you give a small negative reward, the student learns faster. It's like scolding your child instead of letting it fall off the cycle. Okay. So now you can clearly see based on this MDP, the student can learn. Based on this MDP derived, student can learn. Learn with whatever algorithm. Q learning, I had used Q learning, say. Now, if you want teacher to learn, what will you do? And what is its policy? What it is going to learn? This is a bit complex, so we'll not go into details of it, but I'll give you the overall idea. Students learning is clear, right? Once you have the policy, you have the reward function, it can learn using Bellman equation. Clear? Antriksh, you have a question?
So the D's which we get are from the student's experience.
So D's will come out from the teacher. His teachers will get the
No,
experience.
the DI's I understand. And the D?
D is a oracle D. It's not known generally. And the teacher will have an estimate of D based on the student's experience of the world. That's what I'm coming to now. So this authors of this paper have used multiple notations. You can go over it. Students learning or the teacher learning. It's quite simple. So say you observe V pi of student or I of student under the intervention set DI and TI. Okay. So rather not DI and so V pi of this observation state based on the policy of the teacher. I will see what it is. But currently what I'll do is this is the performance. The value function. That is what I'm trying to say. So the value function is the performance. So based on the value function, we can extract features. These people extract features like total reward, then number of times you visit the dangerous state, trajectory length, and so on. These are the measure of how well your student learned. So your value function for the teacher, P pi T for teacher, we can just say as phi transpose V pi I of student transpose into some W. Okay. Based on these value functions, I can estimate the value function of the teacher. And pi T is what I will learn is from the hypothesis space or whatever feature space that I have. That features that I have, features to the set of interventions. So I'll say these interventions include DI plus 1, and Ti plus 1. So the model, the teacher will output a new set of dangerous states and a new state of reset distribution. Reset, new dangerous. Based on the student policy. Questions may have been unclear.
So this phi of v pi of student, that's a function of the v pi, right?
Correct, V pi or the entire trajectory, entire experience of the student, entire history.
Okay.
So this thing is often referred to as history in the paper. So entire history, you can extract some hand engineered features. These people at least do that based on the say total number of reward, dangerous states, and so on. Fine.
Okay. And this we do for all the students. Like if there are multiple
Correct.
students.
Very good. That's the piece on the cake. So this is the teacher that I'm learning, teacher. And now what the total algorithm looks like something like this. So the teacher learns over n generations. Just like our society, we don't just learn in one generation altogether. We learn, our curriculum is learned over generations. How well is our society progressing, and these measures are used to devise new curriculum. So use a for I equal to 1 to nt, get a new student, then for the student, have another net loop, number of interactions with environment, do Q learning. So that you write Q pi of the student J. So this is the student. Use Q pi or the history of pi J of the student, some phi trans function to evaluate performance. Then update the teacher policy. Pi T. Q learning in the constrained MDP. MDP of pi T I. Okay. Antariksh, fine. So the student keeps learning over generations. There will be multiple students and the teacher updates its curriculum based on multiple students, which is basically a history to a map of interventions. So with that, we come to the end
This
of
update, so this update phi t is like within the loop, right? Of J.
the outer loop, correct. With it, update phi t can be within the loop, can be outside the loop also. So depending on your implementation inside the loop, if you want to update phi t at every step of the student generation,
Yeah,
or in,
got it.
this can be both in inner
Also,
outer
could you
loop.
just roll back to that position where you're doing expectation of that IET was less than K, the some arbitrary constant, right?
Correct.
Like, no, the before, the good.
So
Like-
what we will end up doing is we will allow the teacher to help only K times. So that's how it will not go to the states more than K times.
Yeah, so we don't want it to be over the restricting or over
Correct.
yeah, either over restricting or over helping. So
Correct. If you're over helping, then what happens? The student is barely able to learn. So therefore, you allow only a fixed number of uh, curriculum inductions,
yeah,
and then you say that it
it's just
decreases
to
over
ensure
time.
that it's just to ensure that we don't have a major like down a major problem issue or like a
Correct.
near death situation, as you said.
Correct. Correct. And don't try out things which are really bad for you and the society. So basically, a good teacher will have a intervention set like this. It's a good intuition to have at the end. When I did this project, I found out a good teacher had this intervention set around this dangerous states. So that these never go to these states. Never goes to a state where it is likely to go to a dangerous state. From understood. So this could be a exemplar DI. And you could just say that once you go to the state, you get back to the back states with a small negative reward. Okay. So that ends our discussion on probability and linear algebras and those two things. Using those two, we have discussed reinforcement learning. And in reinforcement learning, we have talked about starting from all the way from Bellman equation, model-based methods, model-free methods, approximation-based methods, and today all the way to safe RL. So come a long way. What I'll try to do is after, so we have completed now what the teaching part of it. So the rest of the 10 hours that is remaining for us will be just solving these assignments. I'll be solving these assignments and uploading the solutions for you. This is like 6, 8, 10 hours of assignments are there for you. I'll upload the assignment solutions to you. All the 3 assignments, 1 and 2 and 3 clubbed. And you say I'll give you time till the end of mid of July, 15th July maybe, to finish the assignments.
Dada,
And
we have we would be able to complete, but here's the thing, like a lot of my friends are doing the assignment, but uh like they intend to do both the assignments, but the thing is that our exams are from 7th to 18th of July. So if you could
finish it
extend it,
before, no.
uh,
Or
right, so
I can decrease that extension. I can say that, okay, finish it at by 6th of July.
so that's the thing, like they are first we need to cover the our same syllabus as well. I and Shubham can
Okay, okay.
obviously
Let
do
me
that
just stop
according
the
to
recording. Wait. Just wait. See.